We're in Turkey, on the shores of the Dardanelles Strait, and what you see behind me is officially the longest suspension bridge on the planet. The Çanakkale 1915. Its center span, exactly 6,637 feet of symbolism and engineering audacity. When it opened in 2022, that measurement allowed the bridge to surpass Japan's Akashi Kaikyo and become the longest suspension bridge in the world. But here's the thing, it's not just about length. Look at this roadway. It's not concrete, it's pure steel. Today, I'm going to show you how, at the Cimtas Steel factory, they welded together entire chunks of continent that were then hung over the abyss like building blocks. Let's go! To build this giant, engineers decided to ditch traditional methods. They headed to the Cimtas Steel plant in Gemlik. Here, steel isn't just cut. Here, they create mega blocks from it. Picture this. Instead of assembling beam by beam up in the air, the guys at the factory welded together a ready-made chunk of road. One block like this measures 157.5 feet long, 147 feet wide, and 6 feet tall. That's the area of 2 professional basketball courts, welded into one monolith. A single block weighs 700 tons. That's like lifting 5 Boeing 747 passenger jets into the air all at once. When you stand in the workshop next to this beast, you don't see a bridge, you see a steel skyscraper laid on its side. At the heart of this bridge lies what's called an orthotropic steel deck. Simply put, it's a hollow steel box. But what a box! Inside, this block resembles the compartments of a submarine. Every millimeter of the structure is airtight. There are miles of welding seams running through here. A true symphony of sparks. At Cimtas, they used robotic portals that welded steel 24/7. Why such complexity? Because inside the block, a special microclimate is maintained. It's as dry as the Sahara Desert in there, so rust can never reach the heart of the structure. This is eternal steel that doesn't fear the humid sea air of the Dardanelles. When you peer inside one of these blocks, it feels like you've stepped onto a science fiction movie set. Endless steel ribs of reinforcement disappearing into darkness. The welding process starts with the bottom plate. These are massive sheets of special steel laid out on a perfectly flat magnetic floor. But the plate by itself? Just iron. To handle the weight of thousands of trucks, it needs reinforcement. That's where the stiffeners come in. Long steel channels running the entire length of the block. How do you weld them? By hand, it'd take a decade. So instead, a massive portal rolls over the plate. An automated welding station. It looks like science fiction. Dozens of welding heads descending to the metal simultaneously. They move in sync, like the legs of a steel spider. You see dozens of bright points of light crawling along the plate. This is submerged arc welding with multiple heads. The metal melts beneath a layer of special flux so you don't see open flame, but you feel the air in the workshop rumble from the power of those electric arcs. Once the bottom plate is reinforced, assembly of the sidewalls and partitions begins. This is when the box takes on volume. Diaphragms are installed every few feet inside the section. These are the internal skeletal ribs of the bridge. This is where the hardest work begins. Welders go inside the section. Picture this. You find yourself in a steel maze. Above you, the roof of the future roadway on the sides, walls and all around, just the glint of lamps and the sound of metal. Every joint between the internal ribs and outer shell is welded by hand or semi-automatic machines. Everything matters here. Temperature, humidity, the speed of your hand. Why? Because this block has to be airtight. When the top plate, the actual roadway section, covers this structure, they seal the block completely. It's like building a submarine that's going to hang in the air. If even a little moisture gets inside, it'll start eating the metal from within, and you'll never see it from the outside. That's why after welding, every seam gets checked with a vacuum test or X-ray. If there's even one micro crack, they cut out the weld and do it all over again. The most interesting part is the top plate where the cars will drive. That's the orthotropic deck itself. It's a steel plate welded with longitudinal and transverse ribs so that it's incredibly rigid in one direction and slightly flexible in the other. When you look at a finished mega block from the outside, It seems smooth and black after painting. But inside, it's a true lacework of steel. Miles of welds. If you unraveled all the welding seams from one of these blocks into a single line, it would stretch for dozens of feet. And every inch of that line has to withstand the vibration from the wheels of millions of cars over the next 100 years. After the last seam is completed, the block goes to abrasive blasting. The steel is literally bombarded with tiny metal balls to remove scale and prep it for painting. Then, several layers of protection, and these 700 tons in one piece are ready for their journey by sea. Are you ready to subscribe to this channel? Do it now. We move on to the key stage of assembly, lifting the sections. The completed mega block is delivered to the Dardanelles Strait on special pontoons. At this point, all shipping in the strait comes to a complete halt, because the operation demands perfect precision without interference from waves created by other vessels. For the lift, one of the most powerful floating cranes in the world is used, the Asian Hercules III. This vessel is technically a self-propelled heavy-lift floating crane, capable of lifting up to 5,000 tons. To put that in perspective, its hull is over 300 feet long. Its job is to approach the pontoon with the section, secure it, and lift it to the design height of roughly 250 feet above sea level. The lift itself is pure math. The mega block's weight gets distributed across multiple attachment points to avoid any tilting that could warp the steel box. The crane operates at low speeds to minimize wind load impact, which at this height is a critical factor. When the section reaches the right level, it connects with the suspenders running from the bridge's main cables. This is the moment load transfers from the crane to the bridge structure itself, requiring perfect synchronization of all hydraulic systems. Since Turkey uses the metric system, this bridge is packed with symbolism. The length of 2,023 meters is a direct nod to the year 2023, the centennial of the founding of the Turkish Republic. The height of the towers isn't random either, 1,043 feet. These numbers symbolize the date March 18th, meaning the 18th day of the third month, the day of victory in the Battle of Çanakkale in 1915. The total length of steel wire used for the main cables exceeds 531 million feet. That's enough to wrap around the Earth at the equator 4 times. The steel roadway deck alone weighs close to 50,000 tons. The total weight of steel in the project exceeds 100,000 tons. And for the foundations and towers, 8 million cubic feet of concrete was used. That's a volume that could fill a small town with 2-story houses. Don't ask me why the example of filling a town with concrete popped into my head. The Dardanelles Strait is characterized by high seismic activity and extreme winds, so engineers built colossal safety margins into the design. The bridge is engineered to withstand wind gusts up to 174 miles per hour. This was made possible through a split road deck. 2 separate steel box girders have a gap between them, allowing powerful air currents to flow freely through the structure, virtually eliminating the sail effect. As for seismic protection, the bridge supports are based on massive steel caissons installed on the seabed. To ensure stability, the ground beneath them was pre-reinforced with steel piles, 363 of them, each with a diameter exceeding 8 feet. This foundational preparation allows the bridge to safely withstand earthquakes exceeding magnitude 7.0 while maintaining the integrity of all critical connections. If you want to feel like an ant, stand at the edge of this pit. The super pit is a scar on the face of the planet, almost 2.5 miles long. Here, in the red dust of the Australian desert, mechanical gods labor. Caterpillar 797F. Dump trucks. When this monster rolls by, the ground shakes like an earthquake just started. It's as tall as a 3-story building, and its engine pumps out 4,000 horsepower. But today, we're not interested in engines. We're interested in its shoes. Each of these dump trucks runs on 6 tires sized 5980R63. Each one weighs over 5 tons, stands 13 feet tall, and costs as much as a luxury Porsche, anywhere from $40,000 to $60,000 a pop. We're at the graveyard of titans. One of the Caterpillar tires just gave up the ghost. After 7 months of hellish work under 400 tons of load, on the scorching desert rock, its tread has worn down to a dangerous level. The giant can no longer roll. The process begins, what the industry calls off-the-road tire disposal, but we'll call it the burial of a giant. You can't just toss this tire aside. Australia has strict environmental laws, and burying this mountain of rubber in the desert is a crime. The tire has to make it to the tire cycle plant in East Rockingham near Perth. That's nearly 400 miles across the scorching outback. Transporting a single tire like this is a special operation all its own. They load it onto a specialized flatbed. It takes up the entire width of the road. Up front, escort vehicles with flashing lights. The giant travels to its final resting place slowly and majestically. Kalgoorlie dust settles on its battered rubber, and the Western Australian sun heats its steel cord until it glows. When we arrive at the tire cycle plant, the smell changes. The red dust of the desert is gone. The air is thick with heated rubber, ozone from the electric motors, and metal shavings. Tire cycle isn't just recycling, it's a high-tech slaughterhouse for machine organs. The oversized tire processing facility hits you with its brutality. No bright signs or coffee machines here. Just concrete, grease, and steel. The chief engineer meets us, a man whose face is carved with wrinkles like the tread of that very caterpillar. See this beauty? He points to our tire, just lifted off the platform. There's enough steel in there to build a small bridge, enough energy to power a small town. But to get it out, we gotta tear her apart. The main problem with the world's biggest tire? You can't shove it into any standard shredder. No machine can handle a solid chunk of rubber 3 feet thick and weighing 5 tons. That's why the first stage is cutting. We approach a massive hydraulic rig the workers call the guillotine. A giant blade made of ultra-strength steel slowly descends onto the tire. The pressure is so intense you can hear the building itself groan. When the blade slices through the tread, there's a sound like a cannon shot. That's the inner layers of rubber exploding, stretched taut from years of work. But the hardest part? The bead ring. Inside every Caterpillar 797 tire is a ring of thick steel cable. It's the anchor that locks the tire to the rim. You can't cut through it with a regular blade. A special manipulator rips this steel heart out of the rubber flesh. Only after the tire's carved into slices, like a giant black watermelon, is it ready for real processing. Next, the chunks head to the primary shredder. This is total vibration territory. You feel it through your heels, straight through the concrete floor. The noise is so intense that even specialized ear protection can't save you. You're hearing the sound with your bones. This shredder is a meat grinder for titans. It's got massive torque. Chunks of a 64-inch tire get transformed into brick-sized fragments. But that's just the beginning. Next comes secondary shredding. Here, the bits get smaller and smaller. That's when the magnetic separation system kicks in. A Caterpillar tire isn't just rubber, it's a complex composite. Tire cycles' magnets snap loudly as they yank out the steel cord. You see thin steel wires that once held the shape of this 5-ton monster flying into a separate bin. This is pure, high-grade steel that metal mills are willing to pay big money for. If you want to hear about the steel too, leave a comment and subscribe to the channel. My next video might be exactly about that, because inside every 5-ton tire there's roughly 2,000 pounds of high-carbon steel. That means recycling just 7 or 8 of these tires yields enough metal to build an entire body for a new dump truck. After the 5-ton giant has been sliced by the guillotine and shredded into brick-sized chunks, we reach the stage where brute mechanical force gives way to high technology and the physics of extreme states. We're moving into the very heart of the tire cycle plant, the cryogenic refining zone. While ordinary rubber crumb produced mechanically has jagged edges and textile cord residue, the cryogenic method delivers raw material of cosmetic-grade purity. But to do this, you have to trick the rubber by stripping it of its main natural property, elasticity. In front of me stretches a long, hermetically sealed tunnel made of stainless steel with white vapor billowing above it. This isn't smoke, it's liquid nitrogen evaporating. Chunks of rubber that just an hour ago were rolling red hot across desert dust now enter this frozen corridor. Inside the chamber, the temperature sits at minus 310 degrees Fahrenheit. This is deep cold territory, where life is impossible and molecular bonds change their very nature. Liquid nitrogen instantly strips heat from the rubber. You hear a distinctive sound, not the roar of a shredder, but a light, brittle crackling. This is thermal shock. At this temperature, a phase transition occurs. The rubber passes through its glass transition point. The rubber can no longer stretch. It can no longer cushion impacts. It becomes glass. At the exit of the nitrogen tunnel, these glassy chunks face a high-speed hammer mill. This is the moment of truth. Because the rubber has lost its ability to absorb shocks, it behaves like a crystal vase. One strike from a steel hammer, and a 5-pound block of former tire shatters into billions of tiny crystals. This isn't cutting, this is total pulverization. This method perfectly separates rubber from the tiniest nylon fibers and traces of metal dust. Metal and textile don't become brittle at these temperatures, they stay intact while the rubber turns to dust. That lets magnets and air separators achieve product purity of 99.9%. What comes out of the cryogenic system doesn't look like trash. It's fine. Velvety black powder, rubber dust. So fine it passes through the tightest screens. I walk up to the big bag where the finished product pours in. This powder feels cold to the touch, almost icy, and incredibly fluid. It doesn't clump like regular crumb because the edges aren't torn. They have perfectly smooth fracture planes like expensive sand. This is our premium product, says the tire cycle engineer, letting black dust flow through his fingers. Regular crumb goes into roads, but this cryo powder gets bought by manufacturers of new tires and high-tech adhesives. They mix it with virgin rubber, and it becomes part of new wheels for those same caterpillars. The wheel literally returns to itself. Standing by the cryogenic chamber, you understand the paradox. To give a tire eternal life, you first have to freeze it to the point of death. It's a clean, almost sterile process. There are no sparks, no smell of burning, only white nitrogen vapor and the rustle of black snow falling into bags. Every year in Australia, over 100,000 tons of these tires wear out. That's roughly 20,000 giant wheels. Before plants like Tire Cycle opened, only 5% got recycled. The rest just piled up in the desert. Old tires in the desert are a ticking time bomb. If a mountain of these wheels catches fire, say from a lightning strike, it's nearly impossible to put out. It can burn for months, pumping tons of toxic soot and zinc into the atmosphere. What if I told you that every gallon of gasoline contains traces of life that existed on Earth millions of years ago? And without it, the modern world would simply grind to a halt. Every year, humanity burns energy born from prehistoric plants, plankton, and creatures that vanished long before humans even appeared. But almost no one knows how a black, dirty mixture from miles underground transforms into a clear liquid capable of powering billions of engines. Inside oil refineries, processes unfold that resemble controlled chaos. Temperatures like inside furnaces, pressures that can tear through metal, and molecules that get broken apart and reassembled. And if you stick around till the end, you'll find out which stage of gasoline production actually determines whether your car will run or not. It all starts with crude oil pumped from underground, sometimes from depths of several miles down. This oil isn't some uniform substance. It's a complex mixture of thousands of different hydrocarbons that formed over millions of years from the remains of ancient organisms. Picture this. Dinosaurs, prehistoric plants, and plankton got transformed under pressure and heat into what now powers modern civilization. Wild fact, right? When oil gets extracted, it looks different depending on the field. It can be almost black and thick as molasses, or it can be lighter and more fluid. Mixed inside are molecules of varying sizes, from tiny gases to massive heavy components. And the refinery's job is to separate this entire mixture into useful products, one of which is gasoline. The first and most crucial stage is called fractional distillation. Crude oil gets pumped into a massive vertical tower that can reach the height of a 15-story building. This tower is called a fractionating column, and it operates on a simple principle. Different substances boil at different temperatures. First, the oil is heated to around 750 degrees Fahrenheit in a special furnace. At this temperature, most components of the crude oil turn into vapor. This hot vapor mixture enters the bottom of the fractionating column. Inside the tower, dozens of horizontal plates called trays sit at different heights. And this is where the real magic of separation begins. When hot vapor rises up the column, it gradually cools down. At each level, the temperature is slightly lower than the one below it. Heavy molecules with high boiling points condense first, at the bottom of the column, where it's still hot. Lighter molecules rise higher until they reach a level with their condensation temperature. There, they turn back into liquid and collect on the corresponding trays. The lightest gases, like propane and butane, pass through the entire tower and exit at the top at temperatures around 90 degrees. A bit lower, at temperatures from 150 to 400 degrees, the gasoline fraction collects. These are the molecules we're interested in. Even lower by temperature, you get kerosene and diesel fuel, and at the very bottom remains heavy fuel for ships and raw material for asphalt. But here's the kicker. If you just separate crude oil into fractions, you don't get that much gasoline, like maybe 15 or 20% of the total volume. And the demand for gasoline is massive, way bigger than what naturally exists in crude. So refiners came up with a clever way to make more gasoline from what they've got. A process called cracking. Cracking is breaking big heavy molecules into smaller ones that work for gasoline. There are a few ways to do this. Thermal cracking simply heats heavy oil to extreme temperatures around 900 degrees Fahrenheit under high pressure. Under those conditions, long chains of carbon atoms literally snap into shorter pieces. An even more effective method is catalytic cracking. Here they use special catalyst substances, usually aluminosilicates, that speed up chemical reactions without heating to such insane temperatures. Heavy oil gets mixed with hot catalyst powder at temperatures around 1800 degrees Fahrenheit, and the molecules split way faster and more efficiently. After the reaction, the catalyst gets regenerated and used again and again. There's also hydrocracking, where on top of high temperature and a catalyst, they add hydrogen under pressure, up to a ton or even 1,500 pounds per square inch. Hydrogen helps clean up the molecules, removing sulfur and nitrogen that can be harmful. This process produces the cleanest, highest quality gasoline. But even after all these transformations, gasoline still isn't ready to hit your tank. You need to improve its properties through processes called reforming and alkylation. Reforming changes the structure of gasoline molecules, increasing its octane rating, a measure of how resistant the fuel is to knocking in the engine. Low-octane gasoline can ignite prematurely in the engine cylinders, causing a knocking sound and potentially damaging the motor. During reforming, gasoline molecules pass through a series of reactors with platinum catalysts at temperatures around 900 degrees. There, straight chains of atoms rearrange into branch structures and ring molecules, which have higher octane ratings. Lead used to be added to boost octane, but it turned out to be toxic and polluted the environment, so it was phased out back in the 1990s. Alkylation is the process of combining small molecules into bigger ones, but perfectly sized for gasoline. It takes light gases created during cracking and joins them together using strong acids to make molecules of just the right size with high octane numbers. It's an expensive process, but it produces premium gasoline components. After all these transformations, different gasoline streams get blended in precise proportions to create the final product with the desired characteristics. A bunch of additives get thrown into the mix too, substances that improve various properties. Detergents clean engine deposits. Antioxidants prevent gasoline from degrading during storage. Corrosion inhibitors protect the fuel system from rust. Dyes get added so different types of gasoline can be distinguished visually. In many countries, ethanol is added to gasoline by law, an alcohol made from corn or sugarcane. Usually it's 10% by volume, though sometimes more. Ethanol boosts the octane rating and is considered more environmentally friendly because it comes from renewable sources. though there's debate about whether it's actually that beneficial for the environment, considering all the energy spent growing the raw materials. Interestingly, from 1 barrel of crude oil, 42 gallons, you get about 5 gallons of gasoline plus diesel, kerosene, lubricants, and other products. Nothing goes to waste. Even the gases produced in the process are burned to heat the refinery itself, or converted into other useful substances. A modern oil refinery is a city of pipes, towers, reactors, and storage tanks that can span several square miles. The entire complex is run by computers that monitor thousands of parameters simultaneously: temperature, pressure, flow rates, product composition. A mistake in the settings can cost millions of dollars, or even lead to a catastrophic accident. Environmental standards are getting tougher, so refineries are constantly being upgraded, installing new equipment to clean emissions, cutting energy consumption. Gasoline production has become significantly cleaner than it was 30 or even 40 years ago, though it still remains energy intensive and has an impact on the environment. This entire complex system exists, so you can just pull up to a gas station, stick the nozzle in your tank, and fill up in a couple of minutes. Behind those few minutes stand geologists searching for oil, engineers designing wells and refineries, chemists developing catalysts and additives, technicians keeping equipment running, drivers delivering fuel, a global industry working around the clock to keep the world moving. And while there's a lot of talk right now about electric vehicles and renewable energy, gasoline will remain the primary fuel for billions of cars around the world for a long time to come. It's the product of a century of engineering thought, chemical research, and technological innovation, transforming ancient organic matter into the energy of today.
Imagine a cruise ship taller than 15-story building, longer than 3 football fields, weighing 70,000 tons. Now imagine driving at full speed onto a beach. That's how ships die. Every year, over 700 ocean giants make their final voyage, not to ports, but to demolition beaches in Bangladesh, India, and Pakistan. Workers with blowtorches dismantle these steel leviathans piece by piece, standing where waves meet rust. How does a vessel carrying 3,000 passengers become rebar for apartment buildings? What happens to the swimming pools, the engine rooms, the miles of copper wiring? Stay with us. You'll discover the brutal, beautiful process transforming floating cities into raw materials, and the shocking secret of why 95% of every ship lives again in different form. Our journey begins in Chittagong, Bangladesh, the world's largest ship-breaking beach. The coastline stretches 8 miles, littered with steel carcasses in various stages of dismemberment. From satellite view, it resembles a graveyard of metal whales beached in neat rows. Up close, it's controlled chaos. 15,000 workers crawling over hulls like ants dismantling elephants. The tide determines everything here. Ships arrive during spring tides when water rises highest. Captains gun engines to maximum, driving vessels onto mudflats at 15 knots. The impact shudders through steel bones. When tide retreats, the ship sits stranded, a beached giant awaiting dissection. Workers call this beaching. International shipping calls it the end. Before any cutting begins, the ship must be cleared. Imagine walking through abandoned cruise liner. Swimming pools drained, casinos silent, 3,000 cabins empty. Everything removable gets stripped. Furniture sold to local markets, lifeboats auctioned to fishing villages, artwork shipped to collectors worldwide. The chandelier from the grand ballroom? Now hanging in a Dhaka restaurant. Hazardous materials require special handling. Asbestos insulation wrapped every pipe in ships built before 1990. Workers in basic masks, far below Western safety standards, remove it by hand. Oil residue coats engine rooms inches thick. Fuel tanks supposedly emptied still contain deadly vapors. Last year, 17 workers died in Bangladesh yards from explosions and toxic exposure. This is dangerous work done by desperate men. The cutting begins at the bow. Workers climb scaffolding made from ship parts, wielding oxyacetylene torches, burning at 6,000 degrees. Steel glows cherry red, then separates. Chunks weighing tons crash onto beach sand, shaking ground felt hundreds of yards away. Watch the cutter teams. They work in pairs. 1 torches, 1 watches for falling debris. No hard hats. Flip-flops instead of steel-toed boots. Yet their precision is remarkable. They know exactly where to cut, following structural blueprints memorized through years of experience. "The ship tells you where it wants to break," says one veteran. "Fight the steel wins. Work with it, you go home alive." As the superstructure disappears, the real treasure emerges: the hull. This is where serious tonnage lives. Hull plates measure 1 inch thick, weighing hundreds of pounds per square foot. Cranes, themselves salvaged from previous ships, lift cut sections onto flatbed trucks. The steel heads to re-rolling mills within miles of the beach. Picture the economics. A scrapped container ship sells for $500 per ton. 60,000 tons equals $30 million, split between ship owner, yard owner, and workers earning $3 daily. The math seems cruel, but it's why these yards exist. No Western facility can compete with labor costs. Environmental regulations alone would triple expenses. The engine room reveals industrial archaeology. Marine diesels the size of houses, 12 cylinders, each taller than a man, get disassembled bolt by bolt. These engines ran continuously for 30 years, burning heavy fuel oil thicker than honey. The engineering is magnificent. Crankshafts weighing 50 tons, precisely balanced to spin at 100 RPM without vibration. This machinery doesn't get melted. It gets resold. Ship engines power factories across South Asia. Generators light villages without grid connections. Pumps irrigate farms. The secondary market for marine equipment employs thousands of traders, mechanics, and transporters. Nothing from a ship truly dies. It migrates into developing economies, extending useful life decades beyond original purpose. Below the waterline lies the double bottom, the ship's structural spine. These compartments held ballast water, fuel reserves, sometimes cargo. Accessing them requires cutting through multiple steel layers, descending into spaces never designed for human comfort. Workers joke darkly about the belly, where heat concentrates, air thins, and escape routes disappear. Cutting the double bottom takes weeks. Each section weighs tons, but must be removed carefully. Collapse here buries workers under steel avalanches. Supervisors watch from shore, tracking progress through radio calls. When sections finally break free, cranes swing them clear while workers scatter. The beach cheers each successful lift. These small victories accumulate into complete demolition over months. The propeller comes last and commands highest prices. Bronze propellers weighing 40 tons contain copper, aluminum, nickel, and manganese in precise alloy. Scrap value exceeds $200,000. Yards guard propellers like treasure, storing them in secured compounds until specialty metal dealers arrive. Watch the propeller removal. It requires precision cutting around the shaft, then carefully lowering the massive bronze flower onto reinforced trailers. One slip damages blades worth thousands each. The journey from beach to foundry happens under armed guard. Bronze theft funds criminal operations throughout the region. When finally melted, this propeller might become electrical wiring, plumbing fixtures, or musical instruments. The ship's heartbeat transforms into civilization's nervous system. Shipbreaking emerged from necessity after World War II. Hundreds of Liberty ships, hastily built for wartime cargo, became obsolete overnight. Scrapping them created the modern industry. Taiwan dominated through the 70s, then Korea, then China. Environmental regulations pushed the trade to South Asia by the 90s. Chittagong rose because geography cooperated. Extreme tidal ranges, 16 feet between high and low, create natural dry docks. Sandy beaches cushion impacts. Cheap labor, minimal regulation, and proximity to steel-hungry construction markets completed the equation. Today, Bangladesh breaks 40% of global tonnage. The industry employs over 200,000 workers directly, plus countless more in supporting trades. Love it or hate it, shipbreaking built modern Bangladesh. Carbon emissions drop 62% using ship-sourced steel versus virgin ore production. Industry recycles 20 million tons of steel annually, enough to build 4,000 skyscrapers. A single aircraft carrier yields enough metal for 15 apartment towers housing 50,000 people. Here's the secret we promised. That ship doesn't just get recycled, it gets reincarnated completely. 95% of every vessel finds new life. Steel becomes rebar reinforcing buildings throughout Asia. Copper wiring powers homes. Furniture furnishes restaurants. Lifeboats become fishing vessels. Even the wooden decking becomes flooring in European boutiques, marketed as reclaimed teak at premium prices. From ocean voyager to urban infrastructure, the transformation completes. We've built an ecosystem where nothing truly disappears. That cruise ship where honeymooners danced might now support the hospital where their grandchildren are born. The container ship carrying your television might become the bridge you drive across. Ships don't die on those beaches. They scatter into civilization, becoming the hidden skeleton of modern life. Steel ghosts supporting everything we build.
Every second, factories worldwide produce carbon fiber threads 10 times stronger than steel, yet 5 times lighter. Picture this. A strand thinner than human hair supports weights exceeding 400 pounds, more than 2 adult humans hanging from a thread, invisible at arm's length. These black filaments, woven into composites, form invisible to radar bombers, Formula One monocoques surviving 200-mile-per-hour crashes, and prosthetic limbs outperforming natural bone. How does ordinary plastic transform into materials stronger than steel through fire? Why do engineers call carbon fiber the black aluminum, revolutionizing everything from spacecraft to tennis rackets? Stick around till the end. You'll discover the jaw-dropping reason carbon fiber doesn't break like metal but unravels like fabric, why recycling it became a technological arms race, and the shocking truth about what happens inside furnaces hotter than volcanic lava when atoms reorganize into crystalline perfection. The story begins with polyacrylonitrile, pan fiber, the plastic precursor looking like white cotton thread. Massive spinning machines, standing 3 stories tall in climate-controlled facilities, extrude molten pan through spinnerets containing 50,000 microscopic holes. Each hole, measuring 3/10,000ths of an inch across, thinner than blood cells, produces one continuous filament. Picture spider silk production scaled to industrial extremes. These filaments emerge at speeds reaching 3,000 feet per minute, fast enough to cross football fields in seconds. Chemical baths stretch the fibers, aligning polymer chains parallel to fiber length. This molecular orientation determines everything. Randomly oriented polymers create weak thread. Aligned chains create strength rivaling steel. Workers monitor tension constantly. Variations of 2% cause inconsistent properties requiring entire batches, thousands of pounds worth, to be scrapped. The pan production facility operates 24/7, producing 50 tons daily, enough fiber to circle Earth's equator if laid end to end. Next comes oxidation, the first transformation where chemistry becomes alchemy. Massive ovens, stretching 200 feet long like horizontal tunnels, heat pan fibers to 500 degrees Fahrenheit in pure oxygen atmosphere. Inside these furnaces, oxygen atoms attack carbon-hydrogen bonds in the polymer backbone. Hydrogen burns away as water vapor, leaving behind carbon-nitrogen ladder structures stabilized through cross-linking. This stabilization process takes 90 minutes as fibers crawl through ovens on tensioned rollers. Temperature control matters critically. Too hot, fibers ignite catastrophically. Too cold, cross-linking remains incomplete, causing failure during subsequent heating. The oxidation chamber maintains oxygen concentration at 23% with tolerance of 0.5%. Operators monitor fiber color constantly, watching white pan transform through yellow to dark brown. That color change represents chemical metamorphosis, polymer becoming something fundamentally different, no longer meltable, now heat-resistant enough to survive temperatures that vaporize aluminum. Giant carbonization furnaces, operating at temperatures exceeding 3,000 degrees Fahrenheit, complete the transformation. These aren't ordinary ovens, they're inert atmosphere chambers purged with nitrogen gas, creating environments where oxygen molecules cannot exist. Inside this oxygen-free inferno, stabilized fibers lose nitrogen, hydrogen, and other non-carbon elements through thermal decomposition. Only carbon remains, reorganizing into graphite-like crystalline structures. The process occurs in stages. First, furnaces heat fibers to 2,700 degrees, driving off 90% of non-carbon atoms. The fiber shrinks 25%, density increasing as material compacts. Second stage furnaces push temperatures to 4,000 degrees for graphitization, the process aligning carbon atoms into perfect hexagonal sheets stacked like microscopic playing cards. This crystalline perfection gives carbon fiber its extraordinary properties. Processing takes 3 hours, crawling through furnace sections totaling 1,000 feet long. One power interruption, one oxygen leak, and fibers oxidize catastrophically, burning like magnesium flares, destroying millions in equipment. Now comes surface treatment, electrolytic oxidation creating reactive sites for resin bonding. The carbon fiber, now black as obsidian and measuring just 0.003 inches diameter, passes through electrolyte baths while electric current flows through it. This electrochemical attack roughens the fiber surface at nanometer scale, creating anchor points where epoxy resins chemically bond. Picture this: untreated carbon fiber in epoxy resin slides apart like oiled rope, strong individually but weak as composite. Surface-treated fiber bonds molecularly to resin, creating integrated structure where fiber and matrix function as single material. Modern aerospace composites achieve interface strengths exceeding 12,000 pounds per square inch, meaning the bond between fiber and resin is stronger than many metals themselves. This step is critical because composite strength depends not just on fiber properties, but on load transfer efficiency from matrix to fiber. Poor surface treatment causes delamination, layers separating under stress, the characteristic failure mode making carbon composites unravel rather than fracture. The sizing application follows, coating fibers with protective polymer layer. Massive rollers submerge fiber tows, bundles containing 12,000 individual filaments through sizing baths containing proprietary polymer formulations. This coating serves triple purpose: protects fibers during handling, improves resin wetting during composite layup, and provides limited abrasion resistance. Workers wind treated fiber onto spools holding 10 miles of continuous filament. These spools, weighing 200 pounds each, ship to composite manufacturers worldwide. Quality control inspects random samples continuously. Tensile testing machines pull individual fibers until failure, measuring breaking strength, elastic modulus, and elongation. Modern aerospace-grade carbon fiber withstands stresses exceeding 800,000 pounds per square inch, 50 times stronger than structural steel. The fiber stretches only 1.5% before breaking. Steel deforms 300% more. That limited elongation explains why carbon structures crack suddenly rather than bending. No warning, just instantaneous failure when stress exceeds capacity. After arriving at composite manufacturers, fibers get woven into fabrics or used as unidirectional tapes. Automated looms, programmed like textile machines but operating at glacial speeds to prevent fiber damage, weave intricate patterns. Plain weave creates checkerboard appearance, twill weave produces diagonal patterns, satin weave maximizes smoothness for aerodynamic surfaces. Each weave pattern offers different mechanical properties. Engineers select patterns matching stress directions. Picture this: laying up carbon composite resembles origami, with materials costing $300 per pound. Technicians cut fabric patterns, stacking layers in precise orientations. Each ply orientation, 0 degrees, 45 degrees, 90 degrees, contributes specific strength characteristics. A typical aerospace laminate contains 40 plies, each 0.005 inches thick, creating structures 8 inches thick, yet lighter than equivalent aluminum. Between each ply, workers brush epoxy resin, ensuring complete fiber wetting. Air bubbles trapped between layers become stress concentrators, causing catastrophic failure. So layup occurs in clean rooms, maintaining air purity rivaling semiconductor fabs.
Curing transforms wet layup into solid composite through heat and pressure. Massive autoclaves, pressure vessels 30 feet in diameter and 100 feet long, create environments combining 300 degrees Fahrenheit and 100 psi pressure. Inside these industrial pressure cookers, epoxy resin chemically cross-links while pressure squeezes out excess resin and air voids, compacting layers into dense laminates. The cure cycle takes 8 hours following computer-controlled temperature and pressure ramps. Heat too fast, resin boils, creating voids. Heat too slow, productivity plummets. Modern autoclaves monitor 200 sensors simultaneously, adjusting conditions to within 1 degree and 0.5 psi. After curing, parts exit as rigid structures, material properties now locked permanently. Non-destructive testing using ultrasound and X-rays searches for defects. Even microscopic voids or delaminations require part rejection because carbon composites tolerate 0 defects. Unlike metals tolerating small cracks through ductility, carbon composites fail catastrophically once cracks initiate. That brittleness demands perfection during manufacturing.
This technology emerged from 1960 space race. Thomas Edison experimented with carbon filaments in 1880s for light bulbs. But modern carbon fiber originated when British researcher William Watt developed pan-based process in 1963 at Royal Aircraft Establishment. The breakthrough enabled high-strength fibers commercially viable. Formula One adopted carbon fiber in 1981 when McLaren built the first composite monocoque chassis. Driver John Watson walked away from a 200-mile-per-hour crash at Monza, the carbon tub protecting him despite complete car disintegration. That demonstration convinced aerospace industry. Boeing's 787 Dreamliner, entering service in 2011, uses 50% composite materials by weight. Wings, fuselage sections, tail, slashing fuel consumption 20% versus aluminum equivalents. The B-2 Spirit stealth bomber, revealed in 1989, incorporates carbon composites extensively. The radar-transparent properties, combined with geometric shaping, create aircraft virtually invisible to detection. Today, carbon fiber production exceeds 120,000 tons annually, growing 15% yearly as industries discover applications from wind turbine blades to bicycle frames. Carbon emissions drop by 32% when using carbon fiber in aircraft versus aluminum. Lighter structures require less fuel over millions of flight miles. Industry saves over $68 billion annually through weight reduction in transportation. Wind turbines using carbon fiber blades generate 18% more electricity through longer, lighter blades, impossible with fiberglass. So here's the secret promised. Carbon fiber doesn't break, it delaminates. Unlike metal fracturing through crack propagation, carbon composites fail through layer separation. Impact damage creates barely visible surface dimples, hiding extensive internal delamination, while composites require ultrasonic inspection after any impact. That failure mode makes recycling challenging. You can't melt carbon fiber like aluminum. Heating destroys the crystalline structure that provides strength. Current recycling uses pyrolysis, heating composites to 1,000 degrees in oxygen-free environments, burning away resin while preserving fibers. Recovered fibers retain 70% of original strength, creating secondary markets. From plastic thread to aerospace revolution, cycle completes. Carbon fiber represents humanity's ability to reorganize matter at atomic level, creating materials nature never intended. We've learned to cook polymers in furnaces hotter than volcanoes, aligning carbon atoms into crystalline perfection, stronger than any metal, yet lighter than water. That thread, thinner than hair, doesn't just reduce weight. It enables impossible structures. aircraft wings spanning 200 feet without internal support, prosthetics stronger than bone, spacecraft components surviving forces that pulverize steel. We've engineered the future, one microscopic fiber at a time. The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground. Darkness. Explosion. Tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke.
This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousandths of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year.
China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746. But mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.